All right, so up to this point, we have principally focused our attention on open loop amplifier circuits, where the gain and the input output characteristics of our circuits depended on quantities that can vary due to changes in temperature, supply voltage, process variation, and all that kind of good stuff. All right. These dependencies can cause the performance of physically identical circuits to behave differently. So for instance, I'm going to point out you guys because you were working on a lab assignment the other day, last week, where your specific circuit was behaving differently than everybody else's. It had much more noise on it than literally anybody else in the room, even though ostensibly you were using the same type of transistor, same type of power supply, same type of signal generator, same probes, all that kind of good stuff. You were using literally the same equipment in the exact same setup, and the behavior of your circuit differed from everybody else's circuit, probably because of some very small variation in either the way that the power supply was outputting voltages because they had checked everything else. It could have been some sort of small manufacturing error that didn't get caught in the development of that particular BJT. Some little subtle thing caused your device to operate differently than literally all of your peers did, okay? So engineers have developed a process called the application of feedback to help try to mitigate some of those variances. So to keep circuits operating at effectively the same stable operating point, regardless of variances in operating temperature, power supply ripple, or whether or not there are manufacturing errors, okay? So I'm going to start our real discussion here with a couple of signal flow diagrams, all right? So for an open loop amplifier, which is what we've been dealing with to this point, our signal flow diagram might be as simple as this. So let's say that we have some source signal, XS, okay? That signal gets applied directly to the input of our amplifier, which is characterized by its open loop gain, A. This amplifier can be referred to as the feed forward system, where this terminal represents the amplifier input port. And on the right-hand side of the amplifier, we measure some output Y, where this terminal is the amplifier's output port. And this section of the system is what we will refer to as the forward path, right? Our output here, Y, is simply our input signal, XS, times our open loop gain, A. And I'm doing this intentionally generically because in this class, we are going to be dealing with lots of different types of amplifier circuits. And what I mean by that is we might have input signals that are voltages, output signals that are currents, input signals that are currents, outputs that are voltages, and every combination in between. Okay? So we're approaching this very, very generally. So if Everything else is the same, but the open loop gain of our amplifier is slightly different. We're going to get a slightly different output depending on everybody using this type of circuit, right? We fix that by applying feedback. So for a feedback amplifier circuit, we're going to approach this from a signal flow diagram perspective. So this would be a closed loop system. We'd start again with our source signal, XS. And then we're going to have some sort of mixer here. And we're going to talk about this more in a little bit, okay? But our source signal gets applied to some sort of mixer. And in turn, we get some signal XI, which for right now, I'm just going to call XS, okay? That gets applied to the input port of our amplifier. Right. So again, we have our amp input over here. We have our amplifier output. And I'm going to call this Y. And Y is equal still to A times XI in this case. Our amplifier is still a feed forward system. And this part still represents our forward path. And this bit right here is still our amp output. Okay. Now, where things get different is that we are going to take a portion of our output signal and apply it to some sort of feedback network, which I am going to say is characterized by the parameter K, known as the feedback factor. And I want to talk about this very, very briefly here, okay? So this bit right here is our feedback input port. The reason I'm making note of all of these input and output ports is because in roughly 2 class meetings, we're going to start looking at input-output network parameters of these guys to help us in our analysis. Okay. All right, so before we move along from here, this feedback factor K, in a lot of textbooks, including the one that I have chosen for this class, it's actually written as beta. But because we're going to be talking about transistor amplifiers, potentially BJT amplifiers, having 2 different betas, one representing the common emitter current gain and the other representing a feedback factor would be wildly confusing. So I am arbitrarily just using the capital letter K here as a generic scaling factor that represents our feedback, okay? So in the textbook, if you look through that or several different online resources, you will probably see this written as beta. I am intentionally not doing that because I feel like it would be too damn confusing. All righty. So our feedback network outputs a signal, okay, that I am going to call XF for feedback, and it is simply K times our output signal, Y. Okay. So this is our feedback output. This is what we're going to call our feedback path. And K represents our feedback network. Our feedback network here is typically realized using some combination of passive components, so resistors, capacitors, and inductors. All right. So we've come back around, we've completed our loop, and we're back around at the mixer. So let's talk about that guy. Okay. What it does is it adds our source signal XS, and it combines that with our feedback signal so that we're going to have XS plus or minus XF. Okay. If the sign on this combination is positive, we get positive feedback. If the sign on it is negative, we have negative feedback. Okay. So we've talked briefly about our feed forward system and amplifier characterized by its open loop gain A. We've talked briefly about its feedback network characterized by its feedback coefficient K. A couple of other parts of this system that are pretty important is this node point right here, which I'm going to refer to as our sense mechanism. That's effectively just how we observe the output signal. Okay, so that could be as simple as an open circuit terminal that we can measure voltage across. It could be a resistor there that we can convert current into voltage, something of that nature. So it's just some way for the outside observer to measure and detect the output signal of interest. And this can absolutely just feed into some sort of transducer, which could convert that signal into something that's usable for another amplifier network, if we were so inclined. And then this mixer bit right here is more commonly referred to as the return mechanism. So our general closed loop feedback amplifier circuit consists of 4 distinct parts. Our feed forward system, which connects to our sense mechanism, which in turn connects to our feedback network, which in turn connects to our return mechanism, and then over and over and over again. So that some portion of our feedback signal, which is a scaled version of the output signal, gets combined with the actual signal that we are applying. Okay. So let's talk very briefly about positive feedback first. So in a positive feedback system, a portion of the output signal is added to the source signal. So what's that going to do? It's going to make this input signal Xi larger, which in turn should make our output signal Y larger. So in a positive feedback system, we should see an increase in the system's gain, which we are going to call our closed loop gain AF. Okay. So AF is our closed loop gain. And it can also be referred to as our gain with feedback. So just depending on what textbook you're using, it's typically called these two things. The symbol AF comes from gain with feedback, where A represents gain and F tells you there's feedback. So as always, engineers are boring when we name things. So let's develop a mathematical relationship that will describe what we qualitatively talked about a moment ago. Okay. Our output signal Y is A, our open loop gain, times Xi, which is the input signal applied to the amplifier, right? So we can expand this for a positive feedback system to be A times XS plus XF. And since XF is simply K times Y, this looks like A times XS plus KY. And with a very small amount of algebra, we can define our closed loop gain as our output signal Y divided by our source signal XS, which will become A divided by 1 minus KA. So from here, it's pretty easy to see that A will always be larger than 1 minus KA, right? So 1 minus KA is serving to make the overall gain, the overall system gain, larger. Okay. So as a very, very quick numerical example, let's determine our closed loop gain AF for the system in which our open loop gain A is 10 and our feedback parameter K is 0.0999. So if we plug these numbers into our equation, we're going to have 10 over 1 minus 0.0999 times 10, which comes out to be 10 to the 4th power, 10,000. So by applying the feedback system parameterized by 0.099, we get a pretty substantial increase in the system gain. Yes, ma'am.
Is it ever large enough to make that a negative value?
So that is a fantastic question. Potentially, sure. So that's going to get into effectively playing around with the signs in here is what's going to cause either system stability or system instability. And that is the last couple of topics that I intend to talk about in this class, and what I will probably open up with for those of you who got suckered into taking 438 in the fall. So it absolutely is a big deal. Getting very, very ahead of myself here. It's possible to use a feedback network that will have that will give us a negative feedback like response, right? So if K were negative here, we would have A over 1 plus KA, which is characteristic of negative feedback. Because we're actually going to make the gain smaller, and it's going to give us several advantages from that. The problem that we can potentially face is that since our feedback network can be composed of passive components like resistors and capacitors, there can be frequencies where the sign of the feedback switches from negative feedback to positive feedback, and we go from having a stable system over a certain frequency range to an unstable system beyond that point. And then a lot of what real amplifier design gets into is how to move those frequencies that cause instability around. So that's getting way ahead of what we're doing right here, but that's a very, very good question, which I'm not quite prepared to go into a lot of detail on just yet. Okay, so the purpose of this simple example here was to illustrate that we can get a very substantial increase in the overall system gain by applying positive feedback. But there are problems associated with this, okay? So the first problem that we're going to talk about, I'm going to call gain sensitivity, okay? So let's say that we have the same circuit or the same system. We're going to determine our closed loop gain for a system in which A is equal to 9.9. And we're going to hold K the same thing. So before we go forward here, what's the percent change in our open loop gain? 1%. We have decreased our open loop gain by a factor of 1%. Okay? If we plug these numbers in, 9.9 over 1 minus 0.0999 times 9.9. I want you guys to get out your calculator and tell me what this number is to make sure I'm not BSing you. 900.819 is what I got.
Yeah.
Okay. So a decrease in the open loop gain by 1% caused a decrease in the closed loop gain of, by my calculation, 90.992%. So a positive feedback system is incredibly sensitive to changes in parameters, right? A 1% change in our open loop gain caused a 90% change in our closed loop gain. Not exactly a trait we're looking for, right? Another potential problem that we might see would be that the product of K and A were equal to 1, which could absolutely happen, right? So if we established a feedback system, let's look at this guy right here. If we established a feedback system to where we had a closed loop gain of 10 and a K value of 0.1, we would have A over 0, which means that our closed loop gain is infinitely large. What does that imply? Well, it implies that we're going to get an output signal when we don't apply an input signal. We are going to introduce or generate unwanted signals. Now, we've actually talked about this before, not in this class, but back in circuits 2. Do any of you guys remember the astable multivibrator circuit that I made you look at when we were talking about positive feedback circuits in circuits 2? Nobody has a damn clue.
I remember it. It's pretty cool.
You remember it being pretty
I remember
cool.
the name of it.
Okay.
for sure.
It's an oscillator. It had no input. Yeah, it had no input signal whatsoever. If there was even a tiny amount of energy stored in the capacitor, you saw the output voltage swing from VCC minus down to VCC plus and back and forth as that capacitor discharged over your positive feedback network. I think you guys, if you haven't had an astable multivibrator circuit in your 339 lab yet, I think you're supposed to. Maybe you did one in 229, I'm not sure. You should have had a lab on something like this sooner rather than later, but anyway. Maybe not, maybe that's one of the ones that I cut. But I know that we've talked about an oscillator circuit effectively in circuits 2, and it was the positive feedback that made it behave that way. The circuit was structured in such a way that no input signal corresponded to an output. Okay? That's another very, very big potential problem with a positive feedback circuit. Another one that's maybe a little more intuitively obvious is noise. If we have a noisy input signal, we're just going to make the output signal a scaled up version of all of that noise, right? So we're going to have very, very poor signal to noise ratio in a positive feedback circuit, right? So it's for these 3 reasons, right? Gain sensitivity, system instability, and noise amplification that, typically speaking, positive feedback circuits aren't used as amplifiers, right? Effectively, we corrupt the output signal whenever we have positive feedback applied. So now we'll talk about negative feedback. So a negative feedback amplifier in this case, where we're subtracting a portion of the output signal from our source signal XS, what we'll find is that Y, our output, is still A times XI, which is then A times XS minus XF, or A times XS minus KY. And with a little bit of algebra, we get our closed loop gain, or gain with feedback, Y over XS to be A over 1 plus KA. Means we're always making the system gain smaller than the open loop gain. All right. Now, this might be seen as a drawback. And I guess in some instances it technically is, but there are so many positive attributes associated with negative feedback. This is why we use this for the overwhelming majority of amplifier circuits. Okay. So I'm going to list off some advantages here. And then we are actually going to go in detail on a lot of these in our next lecture. All right. So advantages include gain stabilization, also known as gain desensitivity. So we'll see effectively that with negative feedback applied, a small change in the open loop gain causes practically no change in the closed loop gain. We will observe noise and distortion reduction, meaning that negative feedback causes our signal to noise ratio to get significantly better in the overwhelming majority of applications. We will observe bandwidth extension, meaning that our amplifier maintains its mid-band gain over a longer or larger range of frequencies at the cost of lowering what that mid-band gain is. We will observe input and output impedance modification. So typically speaking, we will see that our input resistance increases by a very large factor and our output resistance decreases by a very large factor, making our feedback amplifier behave more like an ideal amplifier. And then we will also observe an improvement in the circuit's linearity, which this kind of goes hand in hand with the bandwidth extension. Okay. So those are the 5 advantages. They are huge in creating stable and repeatable operating points in an amplifier. The only disadvantage is that the gain gets smaller. So negative feedback is overwhelming choice to use for feedback amplifier circuits. And we are going to focus all of our attention on negative feedback and how to maintain negative feedback in instances where certain frequencies can cause our system to behave like a positive feedback system. All right, so before we get into the nitty-gritty of describing and defining these properties, I want to go back briefly and look at this expression, okay? Because it has 2 important things buried inside of it. All right. The first important thing is this quantity 1 plus Ka, which will be referred to as the amount of feedback. This will be a common factor that helps us quantify effectively all of these improvements. We will see quantities increase by a factor of the amount of feedback or decrease by a quantity of the amount of feedback. So this representation 1 plus Ka as a number effectively tells us the magnitude of the improvements that we see. And then Ka by itself is what's known as the loop gain of the system. And it's kind of obvious, I'll scroll back down as to why. If we just follow our signal, it goes from A to K, so it's just these two things multiplied together. That's the gain of the loop. Okay. The loop gain is the principal characteristic parameter of a feedback amplifier circuit. And so what I mean by that specifically is actually something that Julia touched on a moment ago. When that quantity K times A is positive, we have a negative feedback system. When K times A is negative, we have a positive feedback system. That seems intuitively backwards, but it's because it's in the denominator that it works out, right? So when Ka is positive, the gain goes down. When Ka is negative, the system gain goes up. All right. For very large loop gains where Ka is much, much greater than 1. So I'm going to come down here below what I've written. So for Ka much, much greater than 1, our closed loop gain AF, A over 1 plus Ka becomes approximately 1 over K, which we will define as AF ideal. So what this means is that for very, very large loop gains, the gain of the system is completely independent of the open loop gain of the amplifier. Instead, it is entirely based on our feedback parameter. Where have we observed this? Op-amp circuits, right? For a negative feedback op-amp circuit, our gain depends only on the resistors that we connect to the op-amp, not on the open loop gain of the op-amp at all, right? Or if it does, it's got a very, very small contribution when we're using the practical op-amp parts. Okay? Another consequence of when the loop gain is large is that our amplifier input signal, Xi, will become Xs over 1 plus Ka. It'll be approximately 0. So recall just really briefly here, AF is supposed to be Y over XS, right? Well, Y is A times Xi, and we would normally have an A here. So this is just rewriting this equation, dividing both sides by A, and then multiplying both sides by XS. But what we observe here, the input signal for our amplifier is 0, which is again exactly what we observed in negative feedback op-amp circuits, right? What's the two rules for ideal op-amp behavior? First one, no current can flow into or out of the output terminals. Well, that's because there's a huge honking resistance there, usually on the order of mega ohms to tera ohms. The second rule, no voltage difference between the inverting and non-inverting input terminals, or the size of our input signal is 0. That's because of negative feedback specifically. Okay. So a lot of the stuff that we're seeing here, I'm trying to relate it back to things that we've done before, and then we're going to talk about how it specifically applies to transistor circuits. Okay. So because the loop gain is such a very important parameter for the behavior of a feedback circuit, we have to be very careful and very explicit in how we calculate, okay? So calculating loop gain, A, all right? Step 1, we set XS equal to 0. Step 2, we break our feedback loop at a location such that K and A do not change. So effectively, we have to make sure that our feedback network isn't going to load the amplifier. Okay. So for our signal flow diagram, that would look something like this. We would apply a 0 signal at our input. That's a plus, that's a minus. Here's our amplifier characterized by its open loop gain A. And we're going to break this open here. So there's our break in our feedback loop. And then down here is our feedback network K. Like so. And what we do is we apply a test signal to the input of the feedback network. So I'm going to call this XT for a test signal. And we measure the return signal at the output of the amplifier. Where XR here represents our return signal. And then finally, so we can see just by following our signal flow diagram here, that we'll have a signal of XF is equal to K times XT here. We will have a signal XI, which is just negative. Sorry, I didn't mean to erase that. K XT, and then XR is A K X T, a negative sign. And from this, KA is simply negative XR over XT. So let's start with something familiar. An op-amp circuit, and use it to calculate some parameters here. You good? All right. So let's say that we have the following op-amp circuit. This is our source, Vs. We might have some source resistance, Rs. And we have an op-amp characterized by its open loop gain, A. This is the inverting input terminal. This is the, excuse me, the one with the plus is the non-inverting input terminal. The one with the minus is the inverting input terminal. And so the input signal of the amplifier, VI, is the differential voltage, right? We're literally treating this just like we treated it in circuits 2. We're going to have feedback formed simply by a wire. So we are taking some portion of the feedback signal, and it's going to wind up getting subtracted from Vs, which will in turn actually wind up causing Vi to be very, very close to 0. Talked about it at numerous points. And then we will connect our sense mechanism, in this case, a simple load resistor RL, and measure our output voltage V naught of our system. Okay. So we are going to attempt to answer 2 questions. Question A, assuming that the op-amp has infinite, has doesn't have an E on it, I'm sorry. Input resistance. Rn is equal to infinity. And 0 output resistance. R out is equal to 0. Determine K, feedback parameter for this system. And then B, let's say that if A, our open loop gain, is 1,000 volts per volt, let's determine our closed loop gain AF and our amount of feedback 1 plus KA. All right. So what we are going to need to do to apply the techniques that we're going to use in this class is we're going to need to represent our op amp, in this case, by its practical model, right? The practical op amp model had across its input ports, so a pair of input terminals, an input impedance Rn, which in this case is an open circuit. And then it had a voltage controlled voltage source, which took the open loop gain A and multiplied it by the differential voltage, which in this case is VI, right? That voltage controlled voltage source was then in series with the output resistance, which in this case will be a short circuit. And then from there, we simply connect everything else, right? So starting with our practical op amp model, we would have our input voltage to the amplifier, VI, because our resistance, input resistance in this case is infinitely large. I'm just going to leave that as an open circuit for right now. On this side, I have A times VI. That's my voltage controlled voltage source. And this short circuit up here at the top right represents my zero output impedance. So that's my amplifier, right? Now, let's close the loop and attach everything else, okay? So on this side, I should have my resistance RS. My voltage source VS. So, oops. Here is my feedback network, a wire. Here's my resistance, RL. Here's where my output voltage is measured. All right, so our goal here for the first part is to figure out what K is. And in order to do that, we are going to determine our loop gain and figure out K from that, okay? So the first step of determining loop gain from the stuff we just covered is what? Excess equals 0. So in that case, we are going to just short out that voltage source, right? So that we have no signal being added to the system. What's the next thing that we have to do?
Break feedback loop application such that K and A do not change.
All right, so A isn't going to change if we break our feedback loop down here, and I would argue that K is probably not going to change either because it's just a wire. So here is xt, our test signal. Here is xr, our return signal, okay? So what can we see from this guy? All right, so let's start by being explicit here. Xt is a nodal voltage being measured with respect to ground, right? Because we're treating it as if we were applying some voltage at this node with respect to ground and measuring some voltage at this node with respect to ground, okay? So Xt is simply negative VI. What's XR? A times VI. So from this, KA, our loop gain, is negative XR over XT, or negative A times VI. Right, stylus. Over XT, which is negative VI, or negative A. So our loop gain is negative A. So what's K, our feedback parameter? 1. Oh, you're did I screw this up?
KA equals negative XR divided by X.
Negative XR. Yeah, so that should, okay, sorry. No, this should be positive 1. You're absolutely right. So that K is equal to 1. Sorry, I have a extra negative sign in my notes. Thank you for that. So if KA is equal to A, K must in turn be equal to 1. Thank you for catching. We need KA to be positive in this case anyway, because we're supposed to have negative feedback. So thank you very much for catching my mistake. All right, so now part B should be fairly straightforward, right? Our closed loop gain, AF, is A over 1 plus KA, or 1,000 over 1,001, which is 0.999 volts per volt. Which is pretty much exactly what's expected for a unity gain buffer, which is what this circuit is. Hopefully you guys all remember that, right? We should see a gain very, very close to 1 in a unity gain buffer. That's kind of the whole point. All right. And then obviously, the larger our open loop gain is, the closer and closer and closer this gets to actually being 1. For our amount of feedback, well, that's just our denominator here, right? 1 plus KA is simply equal to 1,001. And I'm going to express it in volts per volt, but it should be a dimensional. I'm using it volt per volt in this point because we know that our open loop gain A is measured in volts per volt. All right, so that's how we apply this to something reasonably familiar. Now, let's look at a transistor circuit. So here is our circuit of interest. I'm going to call this resistor RD1. I'm going to have a MOSFET capacitor. I'm going to call this resistor down here RS1. So I ostensibly have some sort of degenerated common emitter amplifier because I'm applying my input signal Vs here and I'm taking my output at the drain. But to make our lives harder and actually apply some sort of feedback, I'm going to introduce another MOSFET. So let's call this guy M1, this guy M2. We're going to ground this guy. Let's have some resistance here, RD2. And then we're going to take a portion of the output signal, V out here, and apply it through some sort of feedback network here. I'm just going to call this resistor RF, like so. And our goal here, actually, let me state explicitly, lambda 1 and lambda 2 will be 0. So we're going to ignore the effects of channel length modulation. Our goal is to determine our ideal closed loop gain and our feedback parameter K, and then determine our loop gain KA. So let's quantify a few things here. Okay. Let's start with what VI in this case is. Okay. So what does a transistor amplifier do? What's its purpose? It converts, in this case with MOSFETs, some small signal voltage, VGS, into a small signal drain current, ID, right? So I am going to call this bit right here VI. Our degeneration resistor, RS1, the voltage drop across this guy is our feedback signal. This might be hard to intuitively understand. So let's press pause on this, and I want to show you something very, very interesting, or at least I find it very, very interesting. Okay, you don't need to write this down at all. But if we have this circuit, Stop erasing when I don't want you to erase. Be out like so. Okay. Our input signal is our gate source voltage. We are controlling our small signal drain current, ID, and we're measuring that small signal drain current by this output voltage, which is just negative ID times RD, right? So our open loop gain in this system is simply negative GM. Actually, a better way to put this. Our open loop gain in this system is GM. And so what I mean by that is we're talking about the ability of the transistor to convert the input signal voltage at the input to a current at the output. And then our sense mechanism is this resistor RD. And because the current's flowing effectively the wrong direction in a small signal sense, that's why our overall system gain looks like negative GM RD. Okay? So our open loop gain in this case is GM, if we're looking at this from a open loop amplifier perspective, and our sense mechanism is that resistance RD. Well, if we were to include a degeneration resistance, so let's call this RD. We're going to take that output voltage and here we have RS. And here we have our source. Let's walk our way through what happens here, okay? So, as Vn goes up, let's quantify this guy right here. Here's our, sorry, I keep writing C, drain current, right? So as Vn goes up, what happens to ID? Does it go up or does it go down? As VGS increases, what happens to ID? It's bigger. If ID goes up, what happens to the voltage drop across RE? RE is carrying more current. Ohm's law tells us that that voltage drop increases, right? So if we had a voltage here, VRE, when our source voltage goes up, our drain current goes up, which in turn causes VRE to go up. Well, VRE going up causes VGS to be smaller. When we hit that opposite thing here, qualitatively following our signal path, that's what tells us that we have a negative feedback system, or at least it's behaving like it has negative feedback. Now, mathematically, the voltage gain that we've dealt with for this particular circuit should be, why am I calling that RE when it should be RS? Maybe that's why you guys were confused. Sorry, my brain is not working as efficiently as I would like it to today. But our voltage gain for this circuit was negative GM RC over, no, RD, dang it. Over 1 plus GM RS. Well, that negative RD is our sense mechanism. So our gain with feedback would be positive GM over 1 plus GM RS, where RS quantifies our feedback network. So while we don't explicitly see a direct connection, the effects are the same as if we had a negative feedback network, okay? Effectively, we have a feedback network that contains an open circuit from the output down to here, and then a resistor from this point to ground. And that's how we're going to start looking at feedback networks in a little bit. We're going to analyze them as what combination of resistors where short circuits and open circuits are fair game as a resistor value to quantify what our K parameter is. But anyway, I just wanted to show you guys this, that we've accidentally been dealing with feedback circuits for a while now in very specific cases. So if we circle back around to here, hopefully it's a little bit more obvious why I'm calling this voltage drop my feedback signal. Okay. So if we want to determine AF ideal and all that kind of good stuff, we need to figure out what K is. Okay. So recall here that K should simply be the ratio of V out over VF. I'm going to go way back to the beginning here to just make sure that we're keeping things consistent. Right? K, actually, I might have written that down upside down. If we manipulate this expression right here, where Y is our output voltage and XF is equal to VF, K should be our feedback signal divided by our output. I did have that. Hold on. So let me write that down. XF is equal to KY. From this, K is equal to XF over Y. All right, it's 1:45. I've confused myself a little bit here in the notes anyway, so I think this is a good place for me to stop and rewire my brain, but we ran out of time anyway. Okay, so what we're going to do so Friday we don't have class because of the Senior Design Expo and all that kind of stuff. You guys are all supposed to be trying to attend that anyway as part of your lab. Some of you have received formal invitations to come hang out at the Industrial Advisory Board meeting. It's occurring in Tech Point Room 302. If anybody else wants to just pop in and say hey and meet your Industrial Advisory Board and all that kind of stuff, you're welcome to do so. Tech Point Room 302 from 8 a.m. until effectively 11:15 a.m. That's when the board meeting is.